Okay, so we've made our oxaloacetate. We've exported it using either the malate shunt or the aspartate shunt into the cytoplasm. Now we want to start figuring out how to make glucose with it, right? All right, so reaction 2 is the beginning of that process, the remainder of the sort of first bypass reaction that gets us around pyruvate kinase going in the other direction. Pyruvate carboxylase was sort of the first step, getting us to oxaloacetate. This reaction 2 is the second part of that bypass reaction. All right, so again, we've now made oxaloacetate. Make sure I put the carbonyl in this time, not the alcohol. That was what I was thinking. Okay, there's oxaloacetate. Now we're going to burn some GTP. Remember in reaction 1, pyruvate carboxylase, we burned some ATP. Now we got to burn some more energy. This time, this enzyme uses GTP, right, to now synthesize a molecule you will remember, hopefully, this trapped enol of that carboxylate, that phosphorylated alpha keto acid known as phosphoenol pyruvate, right? Plus some GDP, right? The other thing you'll notice, hopefully, is something else happened, right? Oops, give me that. Sorry. Right? Something else has happened here. Remember that CO2 group? That's the one we put on, right? Remember there, that was that methyl carbon right there that we just spent all this effort pulling a proton off of and using biotin and making this, right? There's the CO2 group. Guess what we just did with it? It's not there anymore. You see it there anymore, right? We've now got an enol over there, which means we just tossed it right back off, right? The enzyme that runs this reaction is, of course, phosphoenol pyruvate carboxykinase. It's a mouthful. Or PEPCK, often pronounced Pepsi-K, for you Pepsi fans. So the sort of interesting point here is both of these reactions, the pyruvate carboxylase reaction, because we're burning ATP, and the Pepsi-K reaction, these are both thermodynamically favorable steps. Again, I haven't looked these up. I don't know what the actual or cellular free energy values are for these reactions, but they're less than 0, right? Because in both cases, we're burning some pretty significant amount of ATP or GTP. So these are exothermic, these are favorable reactions. They're going to run in this direction because we're burning ATP. But if you look at that, you're like, wait a minute, we went to all that trouble to stick that CO2 group on to make oxaloacetate, and now the very next step, we just turned around and threw it away. Like, that seems expensive. It is expensive. What do you remember about the phosphotransfer potential of that phosphate group on phosphoenol pyruvate? It's high. It's one of the highest phosphotransfer potentials of any molecule in a cell, right? It's significantly higher than ATP. So you can't just use one ATP to make it. That wouldn't work energetically, right? So the energy necessary to make that one phospho ester bond that's sufficient to subsequently do the things we want to go back and do requires a significantly higher input than a single ATP, right? That's why we have to burn ATP in the first step and then GTP in the second step. And remember, you got to do this twice, right? Because you need 2,3 carbon. The goal here is to make glucose. So we got to do this twice, which means 4 ATP equivalents to make the molecules we would need to end up making some ATP, right? Okay, so this is not cheap, right? All right. But as I said, you think about why do you do it? Why would you do that? Why would you do something so energetically expensive? Well, think back to the whole reason because we have tissues that have to have glucose. And if you're going to die, if you don't have tissues that can run on if you don't supply those tissues that run on glucose, okay, you're going to spend some energy making glucose, right? So that's sort of the energetic logic here. All right. So also you remember that phosphoenolpyruvate has a high phosphotransfer potential because that phosphate group traps this molecule in that enol-like state, can't isomerize to the carbonyl until and unless that phosphate group comes flying off, you can't do that, right? Okay, so that's why this guy has such a high phosphotransfer potential. Okay, but we're not going to make ATP with it. That's a great and all, but what we're going to do is we're going to use this molecule, right, to run back up the glycolytic pathway at this point, right? Or I should back up a little bit here because I skipped how this reaction is going to work, the Pepsi K reaction. It's worth looking at the chemistry of this reaction. So here again, there's oxaloacetate. This is going to, with a little acid-base kick, this is basically a beta keto acid, right? It's also an alpha keto acid, depending on which end you're talking about. But relative to the CO2 group we just put on, this is a beta keto acid. That ketone group is beta to that carbonyl group. Remember, those are fairly easy to decarboxylate, right? And so this provides some of that power we need to drive this reaction, right? So this is going to power us right back in to this enol-like state. But instead of using the enol to synthesize a bond, we're now going to use the oxyanion, right? That CO minus, that O minus group, to attack the terminal phosphate on GTP to make that phosphoester and now pin the enol in that activated state to create the intermediate that was coming out of the penultimate step of glycolysis. We've resynthesized it. We've bypassed pyruvate kinase, and we've now come back up here to the point just above where we would have ended glycolysis. Now, imagine we're pumping that pathway, right? We're running pyruvate carboxylase, we're making oxalate, we're pumping out of the mitochondria, and we've turned Pepsi K on, and we're making phosphoenolpyruvate. At the same time, we've turned pyruvate kinase off. What's going to happen to these intervening steps? As the phosphoenolpyruvate builds up, enolase is going to reverse. It's not going to run this way, right? It's going to run this way. And as the enolase reaction reverses and we start rehydrating phosphoenolpyruvate to create 2-phosphoglycerate, phosphoglycerate mutase is going to reverse. These reactions are all close to or even more favorable in the other direction. So what's going to happen is this buildup of phosphoenolpyruvate is going to start pushing these things in this direction. At the same time, the forward reactions have been shut down. So these concentrations up here are going to start to dissipate. And as these now start to run in the opposite direction because we're close to equilibrium or biased that way anyway. We now slide up through 2-phosphoglycerate, making 3-phosphoglycerate, burn some ATP, run the phosphoglycerate kinase reaction in the opposite direction by using some more ATP, make 1,3-bisphosphoglycerate, reverse gap DH, put in some NADH equivalents because we have to in order to turn that ketone group back into an aldehyde, right? To now create glyceraldehyde 3-phosphate, which can be equilibrated by TIM to DHAP. And now we just run aldolase in reverse, and we've crawled all the way back up to fructose 1,6-bisphosphate. So all the steps that you saw going forward, we've now done in the opposite direction and taken phosphoenolpyruvate and made fructose 1,6-bisphosphate. That's pretty cool. Okay, so now we can just jump to the end of the pathway. Once we've got this, we now need to bypass those committed steps at the top of glycolysis, right? Okay, so to do that, we have our last few reactions, right? Which is, I'm just going to call reactions 9 to 11. I'm just going to write them all out because they're relatively straightforward. So these are reactions 9 to 11 of gluconeogenesis, right? All right, so we climbed all the way back up this pathway. We've made fructose 1,6-bisphosphate, right? You remember this from glycolysis, hopefully, right? Fructose 1,6-bisphosphate. Okay, so what we need to start doing is peeling phosphate groups off, right? So this is pretty straightforward stuff. We're going to basically use some water here to now clip that 6-phosphate bond, that the phosphate ester on that 6-hydroxyl. Right? To create, of course, fructose 6-phosphate, right? Right. The enzyme that runs this reaction is, of course, going to be a phosphatase, and it's pretty obvious to imagine what it would be called: fructose 1,6, oops, bisphosphatase, right? Right. So it basically just uses water to hydrolyze that phospho ester bond. Okay. All right. So now we got to move back towards glucose. We're still in the pyranose ring. So we need to isomerize this guy and turn it into a pyranose ring, right? Okay. So next reaction is just going to, of course, take fructose 6-phosphate and isomerize it. Open that internal hemiacetal, right? Move the ketone, tautomerize the ketone group back into an aldehyde to, of course, create our pyranose sugar that we're kind of looking for here, with the phosphate still on that 6 sugar. Which is, of course, whoops, glucose 6-phosphate, right? The enzyme that runs this is the one that's going to bypass the mutase reaction at the top of glycolysis. This is, of course, phosphoglucoisomerase, right? This one is called isomerase, the other one is called mutase, right? But they're basically just going in opposite reactions, but we need 2 different enzymes to do this, right? Okay. Now, in tissues that do not have the job of maintaining glucose supply in a physiologic setting, like a whole organism like us. So in other words, tissues that are gluconeogenic but are not liver tissue or not kidney tissue, gluconeogenesis stops right here with glucose 6-phosphate, right? You've made the glucose, it's already phosphorylated. You can build this back up and use it to either store in glycogen, right? Which is one of the main things you would do. And then get ready for what you would need to do next. But in liver and in kidney tissue, there's one more step, right? Where you now need to get rid of that remaining phosphate group to now make glucose that could be shipped around the organism, right? We clip off that last phosphate group. Again, putting in some water to hydrolyze that phosphoester bond. Right? And the enzyme that runs this, it's another phosphatase. This one's glucose 6-phosphate, or glucose 6-phosphatase. Right? Okay. So again, this gets us then all the way back to glucose. And this enzyme is a liver or kidney enzyme, right? Most other, as I said, tissues that are gluconeogenic don't have this enzyme, right? Okay, so we're back where we started, right? We've gone all the way back up. So let's think about the balance sheet here for running gluconeogenesis, right? So let's sort of consider the overall balance of what we've done. Okay, so we've taken 2 pyruvates, 4 ATPs, right? 2 GTPs, told you this was expensive, right? plus 2 NADHs, all right, plus 6 waters, right? And now made glucose out of it, plus 4 ADPs, plus 2 GDPs, plus, oops, I dropped a, plus 2 NAD pluses. And remember, each of those NADHs was worth 3 glucose each. So that's another 6 ATP, essentially, that we burned, plus 6 inorganic phosphate, and 2 waters. Sorry, 2 protons. The overall free energy for gluconeogenesis is in the range of minus 48 kilojoules per mole. So it's thermodynamically favored, right? It's an exothermic pathway. It will run absolutely, as we've talked about, but it's expensive, right? If you think about that, like I said, we burned 4 ATPs, we burned 2 GTPs, and we burned the equivalent of, in 2 NADHs, as I said, burned the equivalent of 6 more ATPs, right? So if you add up the sort of total loss, so if you imagine the sum, energetic sum of glycolysis and gluconeogenesis, the net, right? If you would go back and look at the balance sheet from glycolysis and you added in the net change between those two, what you find out is that the overall combination of glycolysis and gluconeogenesis is basically something like this: 2 ATP. Let's write this out. Two ATP plus 2 GTP plus 4 water goes to 2 ADP, 2 GDP, and 4 inorganic phosphate. In other words, the combination of glycolysis and gluconeogenesis irretrievably loses energy, which, if you remember your basic thermodynamics, makes sense, right? The second law requires that that is going to be the case. There is no way to directly reverse this process in a real way without irretrievably losing energy. And that's not cheap, right? That's not cheap at all. But like I said, it's a price worth paying if you have tissues that will only run on glucose, right? And so again, let's revisit this question, where this flux is coming from, right? Why would you do this, right? Okay, we sort of recognize that we have to do it, possibly. And I mentioned that one of the main ways you would feed this pool is by making other stuff into oxaloacetate. Now, we don't do this so much. In fact, I'm not sure. From lipid metabolism in certain organisms, pretty sure mammals can't do this, can take propionyl-CoA and turn it into succinyl-CoA. I think there are other ways we can feed succinyl-CoA. There definitely are through amino acid catabolism, but the lipid metabolism that is sort of indicated here is not something I'm pretty sure mammals do. We can feed succinyl-CoA with amino acid catabolism, though. And I've pointed out that we can feed the oxaloacetate pool by breaking down other amino acids. Alanine, others can be converted directly into pyruvate. Some organisms can also take the glycerol backbone of fatty acids and feed them into DHAP. Again, this is something I'm pretty sure mammals don't do. So there are all these different ways, though, to feed carbon equivalents into the oxaloacetate pool, and ultimately into the gluconeogenic pool, right? But in organisms like us, in mammals, like I mentioned, the main flux is coming from two directions. One is the need to convert amino acids when you need to into something that other tissues like brain and or CNS and red blood cells can run on. But there's and so can be an important flux under certain conditions. But under normal conditions, by far, by mass, the largest flux that feeds the gluconeogenic pathway comes from lactate, right? And the reason for that has everything to do with skeletal muscle primarily, right? So skeletal muscle, if you remember, really wants to run on glucose, right? That's the main fuel it wants to run. It wants to run glycolysis, and then it wants to run TCA cycle because skeletal muscle is an expensive tissue metabolically, right? Burns lots of ATP to do all those nice contractions and move things around and beat your heart and make your body breathe and all that kind of stuff, right? So, like I pointed out before, it stores lots of glycogen, right? And it will nibble on that glycogen as it needs to. It brings in glucose from the bloodstream, and it's happily going, and that's all great right up until the point where you actually get stupid in the gym, or you're out in the woods and you run into a bear, right? And you need to climb a tree. And the issue, as we talked about before, of efficiency just doesn't matter anymore. And your skeletal muscle shifts into rapid ATP production, gives up on aerobic metabolism, ignores TCA cycle, runs glycolysis as fast as it can, keeps the critical glycolytic step of GAPDH running by dumping those electrons from the GAPDH reaction into pyruvate to make lactate, right? Okay. But this is where organisms like us can do something cool. So here over in your muscle tissue, like mammals, you know, the bear's coming, you're gonna run, you're gonna climb the freaking tree as fast as you can, you're gonna mobilize those glycogen stores, you're gonna run glycolysis, and you're just gonna run fermentative, homolactic fermentation as fast as you can and make lactate. But what your muscle tissue is designed to do is to basically use the bloodstream and use the liver to sort of offload the metabolism a bit, right? To say, well, there's a lot of really good energy there. It's a real shame to lose that. But for the time being, I don't care. Let's climb the tree. You run glycolysis, you make lactate, and the tissue will pump that lactate out into the bloodstream as fast as it possibly can, right? If you're well vascularized, you don't get sore. If you're not, okay, pH drops and you get sore. But still, muscle tissue is going to pump this out in the bloodstream. The liver is going to take that lactate back up. And this is one of the liver's big jobs, right? All that glucose that the skeletal muscle is burning like crazy because you've hit some desperate need to use your skeletal muscle in a high load way. There's a lot of metabolic investment in that glucose. It'd be a shame to waste it, right? Like excrete it. So the liver doesn't. The liver takes that lactate in and uses the gluconeogenic pathway we just talked about to take that lactate, reoxidize it, take that lactate, reoxidize that alcohol back into a carbonyl, turn it back into an alpha keto acid, and then take that pyruvate, pump it into its mitochondria, and turn it into oxaloacetate, and then run in those hepatocyte cells, run that gluconeogenic cascade to make glucose, which it can then export into the bloodstream. And once you're up in the tree or the bear is gone, your muscle tissue can now take that glucose and reincorporate it back into its glycogen stores. And so basically, and now burn it at whatever rate it feels like more efficiently through glycolysis and into TCA cycle when you don't need to run away from the bear, right? So this is known as the Cori cycle, right? And it's a really important aspect of sort of glucose physiology and the sort of the offloading of the physiologic needs and recovery of muscle tissue into this differentiated tissue of the liver and its ability to then recover those carbon equivalents in lactate, turn them back into glucose, and then re-export them, right? Okay.